Oh, no.
Okay.
However much of one is perpendicular to the other.
All right, so if I have some vector A here, some vector B here, and an angle theta in between them, what is A cross B? You're racing against Carly, who's looking at her notes right now.
Are we setting the I hat and J hat?
Traditional, is that what you're doing?
Yeah.
Okay. I hat, J hat.
And so then you figure out the components of the A vector and the B vector in I hat and J hat.
Okay. Let's, for the sake of this then, let's call this angle here, well, this would be the complement, called theta prime. Let's make A going in the J direction. So I'd have A J hat cross
You,
we're breaking B up into components here.
yeah, I think it's B cosine theta I hat and B plus B sine theta, or theta prime, J hat.
So B cosine theta prime I hat plus B sine theta prime J hat. What is the cosine of theta prime in terms of theta?
The sine of theta?
Yes. So this is A J hat cross B sine theta I hat. If you imagine this triangle here, the hypotenuse is B, it's a right angle. This is theta prime. This angle up here would be theta, or theta would be theta. And so the cosine of theta prime is just the sine of theta, plus B cosine of theta J hat. All right, now how do we do a cross product?
You multiply the parts that are going in the same direction.
And what happens when you take a unit vector and cross product with itself?
It stops being a unit vector. It's like, yeah.
I think two people just said it. What was it? Yeah, it's zero. Because as you said earlier, it's what's you care about perpendicular. So anything in the same direction as itself is not going to produce anything. We'll get you zero. So you do a cross product with the parts that are not the same, which just leaves you with A, B sine theta, J cross I. And what is J cross I?
1.
No.
Okay.
If you'll notice over here, we have a cross product and our result is a vector. That vector is not coming from the cube. Cross product does produce a vector, otherwise known as a vector product, or for the purist, axial vector or pseudo vector product.
And what
Pardon? Let me close the door while you're thinking.
Well, they are perpendicular from each other.
They are perpendicular. I will agree with that.
And so it would be the entirety of both. Or the,
So the product has a magnitude of 1. I will agree with that. But what is the direction of J cross I?
Negative. Well,
Negative
K.
There we go. Now we're on a roll. If you recall, I cross J equals K. Now, what that means, right hand rule, you put your hand in the direction of the first vector, I right here. You want your fingers to curl towards the second vector, which is pointing up, so I cross J is that way. That produces a vector pointing outwards in a right-handed coordinate system. That is known as a right-handed coordinate system where K is pointing outwards. So this is in a right-handed coordinate system, which is what we deal with. But we have J cross I. So we have J cross I points in the opposite direction. So that'll get you negative K. So this becomes negative A, B sine of theta times K. I'm assuming that there's just a flood of fond memories for most of you. I think the only one probably who doesn't have it is Devin, because he missed the first semester course with me. But I'm sure he understands why the rest of you are having a flood of good memories. So when I'm doing a cross product, if I have a magnetic field that's coming out of the board, and into this I throw a proton, is the velocity of the proton perpendicular to the magnetic field?
Yes.
The proton shooting going that way. Let's do another flashback here. When you're talking about, we have to draw three-dimensional stuff now. And so just getting away with drawing arrows doesn't work as well as in the past. So if coming out, the dot represents coming out of the 2D surface, out of 2D surface, and into the two-dimensional surface. So when the magnetic field's coming out, that means or the dots here indicating that it's coming straight at. It's going to basically break down the middle of this table. So the proton's going this way, the magnetic field's going that way. What is the direction of the force on the proton?
Into the board.
So we have two different directions right now.
Because you have this,
All right, so we have up,
this,
down, into the board. Those are the three choices so far.
you're saying the dots are going out,
Dots are going out.
it's going that way, right?
Proton's going that way.
Down. Is, well, if you're using the right hand, that's the left hand. You can't ever do that, right?
Oh.
All right, so
I don't, I'm trying to.
so you're no longer saying into the board.
Yes.
All right, so you now have up and down.
It's not down.
All right, so there seems to be a general consensus that it's up. Consensus. All right, so let's work it out. So we have V cross B, so we put our hands in the right hand in the direction of the first vector, which is that way. I want my fingers to bend in the direction of the second vector.
Still.
It is down.
Wait, what?
It's down.
Yeah, let's make sure we get that cleared up, because this was the type problem. There was one test, and this is one of my regrets. I had a test where I had a whole bunch of these things, and so people were doing a whole lot of right-hand rule stuff in the air. I wish I had filmed it and then set it to music, because it was like hand ballet. It was actually quite beautiful if you look at it from that point of view. Unfortunately, I've now cut down. I've got tired of my 4.5-hour test, and so I thought, well, let's cut out some problems. So there's less of it now. I've missed my chance. Maybe someday we'll go for the 4.5-hour test again. All right, so the velocity is first. Velocity is in that direction. So when my fingers bend, I want them to bend the shortest way toward the second vector. Since the second vector is out,
I can't move my arm that way.
thumb points down. So this proton is going to, the force acting on it will be down.
So I was right at one point.
Yes,
I was right when I used my
several people were right at one point. And again, it is right hand rule, not dominant hand rule. Any left-handed people in here?
Yeah, that is.
Good, good.
Oh, yeah.
Okay.
I'm left-handed.
I still don't know how to do it.
We could have done it a different way. If I established I, J, and K like this, V is in the I direction. B is in the K direction, so I have I cross K. And if you recall the IJK, going in this direction, it's positive, and going in that direction, it's negative. So I cross K, I'm sort of going around the horn, we can also just repeat if we needed to. I cross K is going to the left, it's negative. So down. And if you look at solutions for whole tests, there are various problems where I will present it in the, looking at it from this point of view and then looking from the right-hand point of view. And it does lead to some interesting drawings also on some of the, I've had multiple choice questions where with space for explain and then people trying to draw right hands. Now the textbook does it a slightly different way than I do a number of these things. So just because there are various methods for doing this, pick one and stick with it. Just recognize in class, I'm going to do it a slightly different way right now, and I'm going to flash back to the Sten gun. If you ever watch World War II movies, the commandos, they got their guns.
All those.
Yeah. So we're about to do one of those right now. All right. So the bullet comes out the barrel. That's the direction of the proton. That's the direction. The magnetic field, I got basically three things here. The magnetic field, that's the multiple lines right there. The thumb, the trigger, the thing that forces everything to start happening is the thumb. Put my finger in the direction of the proton, where the bullet comes out. These fingers right here in the direction of the magnetic field. And the thumb points down, the force is down. There are other methods where you use the flat hand and do it that way, where I think it's like that. Magnetic field, direction of the, it's hitchhiking, direction that the proton wants to go, and then you forcing it downwards. That might be the last time you do it that way, but some students just latch on to that method because that's the way it's in the textbook, and some tutors might do it that way. Just it all goes back to how to do cross products. You can always go back to the math because everybody loves math. All right, questions before I make it more complicated? I now send an electron into this magnetic field. What direction is the force on the electron?
Up.
Why?
Because it's opposite from a proton.
Okay. Anyone have a better explanation? Or want to say it's down?
It's the electric field's going forward,
Good. Magnetic field?
right?
Magnetic field's coming out
No,
still.
the electron is the green thing.
This is my left hand.
Oh,
Nikki.
okay, that's the proton.
Does V cross B change?
No, it's down.
Your Q does.
What's that?
Your Q does? That magnetic
Yes.
field?
The Q changes. V cross B is still down, but Q is now negative. So that flips it. So your reasoning that it's the opposite was absolutely right. So don't forget there is a charge up front. So negative is opposite of positive. So the way you want to do the right-hand rule for that is a negative charge flowing that way is very similar, it's very much like a positive charge going the other direction. So if I have a negative charge going this way, I'm going to treat it as a positive charge going that way. Magnetic field is out, force is up.
Could you just use your left hand?
You could, I really hesitate to do that just because I figured, to me, just a right-hand rule is simple enough, but some students get messed up by that. And so if we go with use the left-hand rule now, use the right-hand rule then, if that works for you, go for it.
Cool.
Different color here. proton is now going into the board. What is the direction of the force on the proton?
It's going into the board.
Proton's going into the board, magnetic field's coming out. Or was that are you answering or asking?
Asking.
Yeah.
Okay.
Say it again? What were you just
So magnetic field's going that way, proton's going this way.
0.
Why?
Because they're going, there's no perpendicular component to them. They're going in exact opposite parallel directions. They're both in the K direction. One's just negative.
Okay, yep, spot on. Now let's make it more complicated.
Yay.
I have a proton, just sitting there. What's the force on the proton? Got a proton sitting there and this magnetic field comes along.
Is it 0 because you have no velocity?
Okay,
Or we don't have a formula for it yet because the formula we have is for a charge moving through.
okay. Now velocity is 0, so the formula still holds.
Okay.
All right, so the proton's just sitting there in the magnetic field. Now, I walk towards the proton. Does the proton have velocity now?
And when you see it, yes.
Yeah.
Therefore,
Yes.
therefore,
Therefore, the force is acting down.
let's see, yeah, would be. That last one was just sort of a mind bender. That branches into a topic that we'll hit in about a month and a half, 2 months.
Okay, what would it become?
Pardon?
And what would it become?
Well, the proton's coming at me. So the proton's moving that way.
His perspective is that the proton is moving that way.
All right, all that's well and good. Let's just do a simple plug and chug and then do a more complex plug and chug. All right, so if I have a proton moving perpendicular through a magnetic field coming out of the board, proton moving at 3,000 meters per second through a magnetic field of 0.5 Tesla. Let's see, moving it, I said through, let's just make, let's say that to the right. It's moving through, all right. Proton moving at 3,000 meters per second to the right through a magnetic field of 0.5 Tesla coming out of the board. What is the force on the proton? What is the acceleration of the proton?
Let's say 9.5 T.
That's 0.5, that's,
Oh.
that word was of. Magnetic field of 0.5 Tesla. So first step. Yes, okay. So coming out of the board, we'll draw my dots here. And you draw until you get tired. 0.5 Tesla, okay. And then proton moving to the right, and with the advantage of colors here. So this is 3,000 millimeters per second. Now what? Okay. So if we did the force diagram here, once it enters the magnetic field, the force is down.
And then to find the force, you just put it into the formula.
All right, so how are we gonna, we need to do one other thing first before that.
Okay.
Data,
Sorry?
do you need data? Data.
Did you have numbers already?
It's theta.
Oh,
He
it's
said-
data.
He said theta.
Yeah.
Oh, I heard data.
Oh, no.
Okay. Theta would be 90 degrees.
So then,
Do we need to set I, J, and K?
We need our coordinate system. We know the direction of acceleration, although if we didn't, we could actually bypass that in this problem. But coordinate axes, what do you want to make I, J, and K? Or I and J, and then K is defined.
write it down.
So I to the right, J down. So what is the direction of K?
Into the force.
All right. So plug it into the formula. F is equal to the charge, 1.6 times 10 to the negative 19th coulombs, times the velocity. This is Q, V cross B. What's the velocity?
3,000 meters per second.
I hat.
Yes. Velocity, not speed. Cross, what's B?
0.5 T.
Where's the Tesla?
Oh wait, is B? Oh wait, it'd be going this way, right?
B's going out.
So K, not K.
Negative K. Because we have J being downwards, K is actually into the board. And so negative Tesla K. And so now I cross K. Or I cross negative K, whichever is where you want to bring the minus sign in. What's I cross negative K?
Thank you.
J.
J, all right. So we have now 3,000, so I can do that math in my head. So we have 1,500 Tesla meter per second J hat times 1.6 times 10 to the negative 19 coulombs. And so 1.6 times 1.5 is going to be, it's 2.4 times 10 to the negative 16th.
Yep.
Coulomb Tesla meters per second, J hat. And a Coulomb Tesla meter per second is what? It was 2.4, right?
Mm-hmm.
Okay. There's a one-word equivalent.
That we know already.
Yes. Yes. We're finding a force. It better be newtons. Thus, we now have a newton is a Coulomb Tesla meter per second, and therefore a second is a Coulomb Tesla meter per newton, and we have a new unit of time. There's 60 of those in a minute.
Nice.
So once the proton enters this field, it's going to be forced downward. So what's going to be the new direction of the proton? Did you just make a hand gesture to the answer? Okay, never mind that.
Wait, say again?
So the proton enters, it's gonna be forced downwards, so what's the new direction? Just shortly after it enters.
Down.
All right, so when it's moving down at this angle, what's the direction of the force acting on it?
Still down.
Pardon?
Still.
Ooh, we're
Going
locking down.
Regulations.
All right, so as soon as it's forced, so it comes in and then it starts to be forced downwards. And you're saying it's gonna be now forced in the direction it's moving?
No, like, since this, like, it's going this way, right? We go like that?
Oh, okay, sorry, I was backwards. So it's gonna be forced this way?
Yeah.
So the force acting on it is perpendicular to the velocity. That's what you're saying?
Yeah.
Huh, only if we've seen that before. What is a force that's perpendicular to the movement? Yeah.
Where?
Yeah.
Towards.
No, it's.
All right, you remember what we did in class?
Yes. It's centripetal force.
There we go, it's a centripetal force. So what's gonna happen is the proton's gonna enter the field, and then it's gonna start to curve in a circle. I think those were sounds of happy memories there. So we have forces equal to mass times acceleration here, because the second question is what's the acceleration, so mass times acceleration. So we can now figure out what the acceleration is, if we just know the mass of a proton. So my acceleration would be force divided by mass. So we have 2.4 times 10 to the negative 16th newtons, J hat, divided by the mass of a proton, which is 1.67 times 10 to the negative 27 kilograms. Could somebody look that up, please?
Mass of a what?
Mass of a proton.
Yeah, 1.67 times 10 to the negative 27.
All right.
Yeah.
And so therefore, what is the magnitude of the acceleration? Point something times 10 to the 14. No, 11.
No, 1.44.
All right. So we now have the acceleration. We've already established that it's centripetal acceleration. So what's the formula for centripetal acceleration?
F equals MAC.
Okay.
Sub C.
And A sub C equals what?
Is that,
Pretty glad.
Or the swirl.
I got it. Negative v squared over r.
Yeah, the negative is a directional thing. So V squared over R, that's equal to V squared over R.
What is that called?
yeah, what is it? That's alpha, the Jesus fish.
Oh, yeah. Yes, it's alpha.
What is
The other form, it doesn't have alpha in it, but it'd be omega squared R.
omega?
Okay.
All right, so we can now predict what the radius of the path will be as it goes through this magnetic field. And so we have 1.44 times 10 to the 11th. This is a magnitude here, so I'm going to drop the J hat. So that meters per second squared is equal to the speed squared, and I know the speed, that's 3,000 squared, divided by R. And so the radius would be, well, that's 9 million, 9 times 10 to the 6th, divided by 1.44 times 10 to the 11th. So 2, 6, so 6 point something probably, times 10 to the negative 5th.
6.25.
6.25. Times 10 to the negative 5th, what? Yes? Now recognize that we now have a radius of what the proton would do. If it were more massive, then the acceleration would be smaller, which ultimately would make my denominator smaller, which would make my radius bigger. So if I had to throw a heavier thing through this at 3,000 meters per second, it would not have as tight a turn. The importance in this, in terms of physics, is we can now start take educated guesses at what a particle is. Because all we need to know is how fast the thing is going when it enters the magnetic field. We can control the magnetic field with the equipment. I shoot a particle through it. It will now curve as it goes through. And so based upon the radius, we can now have a pretty decent idea of what it's going to be. Matter of fact, if it curves, if I have my magnetic field coming out, if it curves down, I know it's positive. If it curves up, it's negative. So we now have two big clues here about what the particle is. I know the charge, and I know, I actually have a ratio of charge to mass, which narrows it down considerably. Questions at the moment?
Where did the, for R, where did the, numerator value come from? Is that just?
This, 3,000 squared.
Okay.
I think there's a master set problem where I give the radius and the description of which way it curves, and then give you, I think, this possibility of 8 different particles it could be, and then based upon that information, predict which particle it is. There is a formula in the book. If we just assume that the shot is perpendicular, F is equal to QVB, just looking at magnitude here, that's equal to mv squared over R. And so R would be mv squared over QVB, which is mv over QV. So if I know how fast the particle is going and know the magnetic field, then if I know the radius, I can now predict this ratio of mass